Alright, so let's go ahead and do the next assigned problem, which is number 8. So we're given that one person in 10,000 people has a rare genetic disease. There is an excellent test for the disease and a bunch of more probability. Alright, so again, let's use the tree. In this case, our main line tree is, we have two cases. Either the person has a disease or does not. Okay. So the person that has disease, this is probability of one person out of 10,000. So this is the same thing as 0.0001. So this is the same thing as P of D. And P of not D would be 1 minus 0.0001, which would be 0.9, repeating 4 times. Okay, so again, this would be the probability of not disease. So from here, it branches off again, 2 branches where the test is positive and this one is negative, and also positive and negative. All right, so probability of this is, I guess, 99.9%. So probability of the test being positive for those people who do have the disease is 99.9%. So we're going to write this as 0.999. So what this really means, this is the same thing as probability of P given D. We can find what this is. This is just 1 minus 0.999, which is 0.001. So this is the probability of not positive given disease. All right, so the next given info is 0.02. That's the probability of the test being positive given, sorry, I'm looking at this one. Test being positive given not disease. Okay, so that would be going on here, and that's 0.0002. Yeah. So this is P of positive given no disease. And of course, you guys can do the math. 1 minus this 0.0002 value would be 0.9998. And this is the probability of negative when the disease is not there. Okay, so let's utilize this tree. And part A, we have to find the probability that someone who tests positive has the genetic disease. So this would be P of D given positive. Okay. So we would have to use the Bayes theorem, and let's write this out. Just using the definition, this would be P of D, P of positive given disease times P of disease all over the same thing plus the rest is pretty much simply plugging in the numbers. So probability of positive given D. So we're looking at this, which is 0.999. Okay. This should be multiplied with those people who have the disease, which is 0.0001. Okay. So we have that, and we have the same thing being repeated, plus probability of positive given no disease. So we're looking at this one, which is 0.0002 times probability of not having the disease is 0.999. All right, so if you calculate this, it should give approximately about 1/3, so 0.033. At least that's what I got when I calculated this. So that means that if you were still tested positive, because the disease is so rare, even if you were tested positive, the result of you actually having the disease is only 33%. That's how it could be interpreted as. All right, so that was part A. Now let's do part B. So we have to figure out what part B is asking for. It's asking for someone who tests negative does not have the disease. So this can be written as not D given negative. Okay, and of course, this is another part where we would have to use the Bayes theorem. So this would be not P, not D, probability of not D, all over the same thing. Plus probability of not P given the complement of the complement of D is just D. Okay. All right, now we have to plug in the values. That would be 998 times of not disease. That would be 0.9999. Plus probability of not P given disease, that's this one. So we have 0.001 times 0.0001. If you do this, I get a value that's about 0.999 something. So this means that if you took the test and if it was tested negative, then it's almost 99.99% that you really don't have the disease. And this makes sense because it's such a rare genetic disease that if you were tested negative, then it's pretty accurate that you're not going to have the disease. And even if you were tested positive, then it's still the percent of you actually having the disease is only 33%. All right, so I didn't assign number 9, but I strongly suggest you guys to try number 9 on your own. It's pretty much the same logic. This is an odd number problem, which means you have the answers in the back. So you guys can check the answers, and if you're not getting the answers, then do reach out, and I'll write up the solutions and then give it to you guys. All right, so this one I'll try to do. All right, so let's actually create the tree diagram again. Again, we can't go anywhere further than making the tree diagram for the Bayes theorem. All right, so suppose that 4% of the patients tested at a clinic infected with the avian influenza. All right, so first and foremost, we have the case. We can have the avian influenza or not have that. The probability of having it is 0.04%, which creates not having it is 1 minus 0.04, which is 0.96. So this is P of A, and this is P of not A. From here, all right, so it's another positive or negative. Okay, so this is positive and negative, and this is positive and negative. And 97% of the patients infected with the avian influenza, so given that you were infected, the probability of the test coming out as positive is 97%. So I would have this here, 97. So what this really means is this is the probability of positive, tested positive, when you actually do have the avian influenza. So with this knowledge, we can easily find what this value is because both of these values should add up to 1. So that would be 0.03. So again, this would mean that probability of tested negative while you actually have the avian influenza is 3%. Okay, and let's take a look at the next given. 2% of the patients. So given that you were not infected with the avian influenza, the test coming out as positive is only 0.02. Okay, so again, probability of the test being positive given that you don't have the disease is 2%, which makes the other portion as 98%. All right. I think I'm just going to do A, and I'll give you the solutions for B, C, D, just because it's a repeat of what we have been doing for the past 2 problems. So this would be probability of patient testing positive for avian influenza with this test. So this is asking for avian influenza given positive. Okay. So using the Bayes theorem, this is the same thing as P given A, P of A, same thing, plus P of not A. All right, so the next part is just plugging in the numbers. Probability of positive given A is 0.97 times probability of actually having the avian influenza is 0.04 plus probability of positive given not having the influenza is 0.02% times 0.96. All right, so if you do this, I got a value of 0.67, so that's it. You can either give your answer as this, or it could be interpreted as 67% is the probability that a patient testing positive for avian influenza with this test is actually infected. Okay, so again, I'm not going to do the rest because it's just a repeat of using the Bayes theorem. So part B, if you interpret this, you are trying to find out probability of not A given P. And this answer should be 0.331. That's what I got. And part C is probability of, let's see, testing. So this is A given negative. Okay. And I got this as 0.00127. All right, part B is interesting. It's if you notice, it's the negation of part C. Okay, so what you have to do is, this is 1 minus the part C answer. So now that we know, it's going to be 1 minus 0.00127. That's going to be the answer for D.